Good evening, everyone. Last time I just briefly mentioned about the optimization problem, right? What is the optimization problem? There is a kind of computational problem whose objective is to find the best out of all the possible solutions, right? And just usually when we deal with it, first of all, you need to define the problem in words, right? And the next step, next phase is to reformulate the problem in a form which is more convenient for analysis, right? And I said the conventional operations research approach for doing this is to construct the mathematical model, right, which represents the essence of the problem. And I said mathematical programming model consists of several important factors, which includes decision variable and the objective function and the constraints, right? What is the decision variable? There is the number of variables whose values are going to be determined within the model, right? And based on the decision variable that you defined, you may construct the objective function. That is the measure of performances expressed as a function of decision variable, right? And then, based on the decision variable and objective function, what other things you need to consider is there is the constraints or the restrictions on the variable, right? Whose values are to be assigned to each decision variable, right? And in this class, i.e. 533, we are going to mainly focus on the linear programming, which is a especially important type of mathematical programming model, right? And LP is the abbreviation of linear programming model, right? In which both the objective function and the constraints are all linear functions, right? And as I mentioned last time, today we are going to review some basics of linear algebra, which is required for this class, linear programming class, right? So at first, let's talk about a matrix. What is matrix? I would say a matrix is any rectangular array of numbers. So for example, all of these four expressions are the examples of a matrix, right? And if a matrix A has m rows and n columns, we refer to m by n as the order of the matrix. And typical m by n matrix A may be written as this, right? And the number in the ith row and the jth column of matrix A is called the ijth element of A, and it is written by small a sub ij, right? So for a given matrix A sub 1, 1 would be 4, a sub 2, 1 would be 5, and a sub 2, 3 would be 7, just for example. And sometimes we will use this notation to indicate that A is the matrix whose ijth element is a sub ij. And the column vector is any matrix with only one column, right? That is, any m by 1 matrix would be column vector. And the number of rows in a column vector is the dimension of the column vector. Is that right? So, for example, matrix A may be thought of as 2 by 1 matrix or a two-dimensional column vector, right? And the row vector is any matrix with only one row. So likewise, the number of column in a row vector is the dimension of the row vector, right? So the matrix B is 1 by 3 matrix, or I would say it is a 3-dimensional row vector. And an m-dimensional vector in which all the elements equal 0 is called a 0 vector. So these are 2-dimensional 0 vectors, right, on the bottom of the screen. Next is about the scalar product of 2 vectors. To define the scalar product of 2 vectors, let's suppose we have a row vector u and a column vector v of the same dimension. Then the scalar product of u and v can be defined by this, right? Of course, the first vector u must be a row vector, and the second vector v must be a column vector. And for example, given a row vector u and a column vector v, uv becomes 10 in this case, right? So far it's easy, nothing's new so far, right? Now we will review the arithmetic operations on matrices, which will be used later in this class, okay? First, scalar product of a matrix. So let me just read this. Given any matrix A and any number C, so in this case, a number is sometimes referred to as the scalar, okay? The matrix C times A, CA, is obtained by multiplying each element of A by C, right? So for example, if A is 2 by 2 matrix like this, then 3 times A becomes this, right? The addition of 2 matrices can be defined only if those 2 matrices have the same order. So to obtain the sum of 2 matrices A and B, we add the corresponding elements of A and B, right? So for example, if both matrices A and B are 2 by 3 matrices, then A plus B also becomes 2 by 3 matrix, like this, right? Very easy. Yes?
This will be here if we...
Could you speak up, please?
If this will be different if we added 2 by 3 matrix and 2 by 2 matrix.
Well, you cannot do that, right? Right. So to do the addition of 2 matrices, both matrices should have same dimension, okay? Okay, next is about the transpose of a matrix. So given any m by n matrix A, the transpose of A is the n by m matrix, right? That is, the first row of matrix A becomes the first column in A transpose matrix, right? Likewise, the mth row of matrix A becomes mth column in A transpose matrix. Okay. So for example, for a given 2 by 3 matrix A, the transpose of A becomes 3 by 2 matrix, like this. Is that right? Okay. Next is about matrix multiplication. So given 2 matrices A and B, the matrix product of A and B is defined only and only if the number of columns in matrix A is equals the number of rows in matrix B. So the matrix product C equals AB is performed as follows. Ij's element of C equals the scalar product of row I of A matrix times the column number J of matrix B. Let's take an example. If we have 2 by 3 matrix A and 3 by 2 matrix B, like this, then AB is defined and C will be 2 by 2 matrix, right? Here, for example, the value 5 for C sub 1, 1 is from the product of row number 1 of matrix A and the column number 1 of matrix B. Likewise, the value the value 7 for C sub 2, 1 is from the product of row number 2 of matrix A and the column number 1 of matrix B. Okay? Now let's consider a system of linear equations given by A. So in this system of equation, x of i's are referred to as variables or the unknowns. Okay? And a sub ij's and b sub i's are the constant in this case. The set of equations like A is called a linear system of m equations in n number of variables. So, right? And the solution of a system of linear equations can be greatly simplified by using matrices. Okay? So, to show how matrices can be used to compactly represent the system of equations A, let's consider matrices A, X, and B like this. Then the system of equation A may be written as AX equals B. So in this case, both sides of equation B will be n by 1 matrices or n by 1 column vectors, right? And sometimes we abbreviate the expression B by writing expression of C. Then this expression C is still another representation of expression A, right? So let's consider a simple example for this. So in this case, how would you express this system of equations by using matrix form? It's going to be 3 by 3 matrix, 1, 2, 3, 0, 1, 2, 1, 1, 1. I just take out the coefficient of 3 equations, right, on the left-hand side. And then times 3 variable, x1, x2, x3, equals the right-hand side of 3 equations. Those are 2, 3, and 1. Right? So this is the expression B, right? If you want to use the expression C, then it's going to be 0, 1, 0, 1, 0, 1, 2, 1, 1, 3, 2, 1, and then a vertical bar and 2, 3, 1. Okay? So both of these expressions would be the matrix representation of the given 3 linear system of equations. Okay? Any questions so far? Okay, then next, let's talk about the Gauss-Jordan method. This is the efficient solution approach for a system of linear equations. Okay? And this method is quite important because many of the manipulations used in this method are used in the simplex algorithm for solving the linear programming problems. And using this method, I'm going to show that any system of linear equations must be satisfy one of the following three cases. Okay? And before studying the Gauss-Jordan method, we need to define the concept of an elementary row operation, which is abbreviated by ERO. Okay? And an elementary row operation transforms a given matrix A into a new matrix A prime by using one of the following three operations. Okay? So type 1 elementary row operation is called the row multiplication transformation. That is, each element in a row can be multiplied by a non-zero scalar. And type 2 elementary row operation is called row addition transformation. That is, a row can be replaced by the sum of that row and the multiple of another row. Okay? And the last, number 3, type 3 elementary row operation is called row switching transformation, which means a row within the matrix can be switched with another row. Okay? So let's look at the type 1 elementary row operation first. For example, if you multiply row number 2 of matrix A by 3, then you will get a prime matrix, right? So we've been using the first type 1 row elementary operation, right? Elementary row operation, sorry. And I said type 2 operation tells that a row can be replaced by the sum of that row and the multiple of another row, right? So for a given matrix A, for example, row number 3 of matrix A could be replaced by 4 times row number 2 of matrix A plus row number 3 of matrix A. So in this case, this number 4, for example, comes from 4 times 1 plus 0. Likewise, this number 13 is from 4 times 3 plus 1, right? Lastly, the type 3 elementary row operation tells that a row within the matrix can be switched with another row, right? So for a given matrix A, for instance, if we exchange rows 1 and 3 of matrix A, we obtain a prime matrix, right? And the Gauss-Jordan method solves a linear system of equations by utilizing these elementary row operations in a systematic fashion, okay? Okay, now I will illustrate the method by finding the solution to the following linear system, okay? The corresponding augmented matrix representation is this. Is that right? That's the expression C, right? And suppose that by performing a sequence of elementary row operations on the original linear system, we could transform the original linear system into this, right? And this matrix corresponds to the following linear system, number 4. So system number 4 has the unique solution, which is x1 equals 1, and x2 equals 2, and x3 equals 3. And because the linear system number 4 was obtained from the original matrix, which is expression 2, by a sequence of elementary row operations, we know that both expressions 1 and 4 are equivalent linear systems. Okay? So the x1 equals 1, x2 equals 2, and x3 equals 3 must also be the unique solution to the original linear system, which is expression number 1. Okay? Now I'm going to show how we can use elementary row operations transform elementary row operations to transform a relatively complicated system like expression number 1 into the relatively simple system like expression number 4. Okay? So we begin by using elementary row operations to transform the first column of system number 2 into 1, 0, 0. And then we use elementary row operations to transform the second column of the resulting matrix into 0, 1, 0. Okay? And then finally, we use elementary row operations to transform the third column of the resulting matrix into 0, 0, 1. And as a final result, we will have matrix number 3. Okay? The following sequence of elementary row operations will accomplish these goals. Okay? So first, we multiply row number 1 of system number 2 by 1/2. And then this type 1 elementary row operation is this step number 1. Okay? And then replace row number 2 of A1 by -2 times row number 1 plus row number 2. This result, the result of this type number 2 elementary row operation would be step number 2. And then step 3 would be replace row number 3 of A2 matrix by -1 times row number 1 plus row number 3. Now, the first column of system number 2 has been transformed into 1, 0, 0, right? Now, we need to transform the second column of A3 into 0, 1, 0. So what he did is multiply row number 2 of A3 matrix by -1/3. Okay? The result of this type 1 elementary row operation is like this, step number 4. Next, we need to replace row number 1 of A4 matrix by -1 times row number 2 plus row number 1 of A4 matrix. That's going to be the step number 5. Okay? And then replace row number 3 of A5 matrix by 2 times row number 2 plus row number 3 of A5 matrix. Now, the column number 2 has been transformed into 0, 1, 0, right? And then observe that our transformation of column number 2 did not change column number 1, right? To complete the Gauss-Jordan procedure, we must transform the third column of A6 matrix into 0, 0, 1, okay? So next, what he did is multiply row number 3 of A6 matrix by 6/5. And then replace row number 1 of A7 matrix by negative 5/5 times row number 3 plus row number 1. Okay? And then replace row number 2 of A8 matrix by 1/3 times row number 3 plus row number 2. And result from step number 9, that is A9 matrix, represents the system of equations. X1 equals 1, and X2 equals 2, and X3 equals 3, right? And because system number 4 was obtained from system number 1, where elementary row operations, the unique solution to system number 1 must be x1 equals 1, x2 equals 2, and x3 equals 3. Is that right? So in our previous example, we've used type 1 elementary row operation and type 2 elementary row operation. At this time, you might be wondering why we defined type 3 elementary row operations, that is, interchanging of rows. Okay? To see why the type 3 elementary row operation might be useful, let's suppose we want to solve the following linear system. So to solve this system of linear equations by Gauss-Jordan method, first, from the augmented matrix like this, the 0 in row number 1, the column number 1 means that a type 1 elementary row operation cannot be used to create a 1 in row number 1 and the column number 1, right? However, right after we exchange row number 1 and row number 2, we may proceed as usual with the Gauss-Jordan method, right? So in this way, we could use type 3 elementary row operation. Okay, then some linear systems have no solutions, and some have an infinite number of solutions. Following two examples illustrate how Gauss-Jordan method can be used to recognize these cases. Okay? So we apply the Gauss-Jordan method to the matrix, and we begin by replacing row number 2 of matrix A by negative 2 times row number 1 plus row number 2. And the result of this type 2 elementary row operation is like this. Now, we would like to transform the second column of this matrix into 0, 1. Is that right? But this is impossible. This system is equivalent to the following system of equations. So, like you see here, whatever values we give to x1 and x2, the second equation can never be satisfied, right? So the system number 2 has no solution. And because system number 2 was obtained from system number 1 by use of elementary row operations, system number 1 also has no solution. Okay? Let's consider another example. Let's try to apply the Gauss-Jordan method to this linear system. The augmented matrix form of system number 1 is this, right? And we begin by replacing row number 3 by -1 times the row number 1 plus row number 3. And then next we replace row number 1 by -1 times row number 2 plus row number 1. And next we replace row number 3 by -1 times row number 2 plus row number 3, right? Next, we would like to transform the third column of A3 matrix into 0, 0, 1. But again, this is not possible. The linear system corresponding to A3 matrix is this, right? And in this system of linear equations, we have 3 unknown variables, but we have only 2 equations, right? Which means there exists an infinite number of solutions for this linear system. Is that right? So to describe the set of solutions to AX equals B, we need to define the concepts of basic and non-basic variables. So for any linear system, a variable that appears with a coefficient of 1 in a single equation, and a 0 coefficient in all other equations is called a basic variable. And the variable which is not a basic variable is called a non-basic variable. Okay? We're going to use this definition for the rest of our classes. Okay? And let's suppose the capital BV represents the set of basic variables, or A prime X equals B prime. And capital MBV represents the set of non-basic variables. And the character of the solutions to system A prime X equals B prime depends on which of the following 3 cases occurs. Okay? So let's look at the first case, case number 1. The linear system has no feasible solution. So this is the example number 3 covered earlier today. So in this example, the second row has the form that each term in left-hand side is all 0, but the right-hand side is non-zero, right? Which means that both systems 1 and the system number 2 has no solution. Is that right? What about the second case? This is the case that the case number 1 does not apply, and the set of non-basic variables is empty. But the linear system will have a unique solution. So to illustrate this, we record the first example, which has been covered early today. So in solving system number 1, the Gauss-Jordan method yielded this matrix in step number 9, right? So in this case, the set of basic variables would be x1 and x2 and x3, and the non-basic variable is empty. And the unique solution to AX equals B is x1 equals 1, x2 equals 2, and x3 equals 3. So for any linear system, a variable that appears with a coefficient of 1 in a single equation and 0 coefficient in the other equations are called the basic variable. Okay? What about the last case, case number 3? This is the case that the case number 1 does not apply and the non-basic variable is non-empty. So in this case, AX equals B has an infinite number of solutions. So to illustrate this, we record the example number 4 covered today. Because case number 1 does not apply, and the basic variable set would be x1 and x2, and non-basic variable is x3. We have an example of case number 3. Okay? So in this system of linear equations, we have 3 unknown variables, but we have only 2 equations, right? So we may conclude that there exists an infinite number of solutions for this linear system. So our discussion of the Gauss-Jordan method is summarized in this figure, okay? And because the end result of the Gauss-Jordan method must always be one of cases 1, 2, or 3, we have shown that any linear system will have no solution, a unique solution, or an infinite number of solutions. Okay? Next is about linearly dependent and linearly independent. Like it says, a set of vectors x of I is said to be linearly dependent if there exist m numbers, some of which are not 0, and which satisfies these linear equations. Otherwise, the set is said to be linearly independent. Okay? So to illustrate, let's consider three 1×3 matrices, which is x1, x2, and x3, like this. And here, x1 and x2 and x3 are linearly dependent. Because there exist 3 numbers. They are not 0. That is, C1 equals 2, C2 equals 3, and C3 equals -1, which satisfies linear combination of vectors which equals 0. Okay? Also, note that this equation implies that x3 equals 2x1 plus 3x2. So x1, x2, and x3 can be interpreted as being linearly dependent. Because one of them, x3 in this case, is a linear combination of the others. Is that right? Let's consider a set of vectors V like this. Then V is a linearly independent set of vectors. To see whether the given set of vector V is linearly independent or not, we need to check if there exist scalars, C1 and C2, which satisfy this equation. And at least one of them should be non-zero if linearly dependent. Is that right? However, in this case, both C1 and C2 must be 0 to satisfy this equation. This is the only linear combination of vectors in V, which is 0. So V is a linearly independent set of vectors in this case. Is that right? Okay, then let me ask you. In this case, V is linearly dependent or linearly independent? Right. So in this case, V is linearly dependent set of vectors. With 0 for the values of C1 and C2, this linear equation can be satisfied, right? However, also with non-zero values for C1 and C2, this linear combination can yield 0. So V is a linearly dependent set of vectors. And alternatively, if we set V1 is 1, 2, and V2 is 2, 4, then V2 can be expressed by V1, and vice versa. So we could say that V1 and V2 can be interpreted as being linearly dependent. Okay? Okay, next, let's talk about the rank of a matrix. Let me just read the screen. The rank of a set of vectors is the largest number of linearly independent vectors that can be chosen from the set. And let the A is any n by n matrix and denote the rows of A by R sub 1, R sub 2, up to R sub m. And also define R is the set of R sub i's. Okay? And let's consider an example. In this case, rank A is 0. Because for the set of vectors, R is 0, 0, and 0, 0. Operator, I'm sorry, but could you locate the camera on the overhead project? Okay. Thank you. So it is impossible to choose a subset of the R that is linearly independent, right? Okay, what about this case? In this case, rank of A is 1. Because in this case, R would be 1, 1 and 2, 2. Right? So if we try to find two linearly independent vectors in R, we fail. Because in this case, 2 times 1, 1 minus second element 2, 2 becomes 0, 0. Okay? This means that rank of A cannot be 2. So rank of A must equal to 1 in this case. What about the next case? Here, this case, R would be 1, 0, and 0, 1. Is that right? And we know that R is linearly independent set of vectors. So in this case, rank of A would be 2. Does this make sense? Next, let's talk about the square matrix. What is square matrix? A square matrix is any matrix that has an equal number of rows and columns, right? Then what is diagonal elements? The diagonal elements of a square matrix are those elements a sub ij such that I equals j, right? Then what is identity matrix? Identity matrix is a square matrix, right? Always, in which all the diagonal elements are equal to 1, and all non-diagonal elements are equal to 0, right? And usually, I sub m represents the m by m identity matrix, right? So for example, if I have I sub 2, this is going to be 1, 0, 0, 1, right? And I 3, I sub 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? It's pretty easy. Okay, then next is about inverse of a matrix. To solve a single equation like 4x equals 3, for example, we simply multiply both sides of the equation by the multiplicative inverse of 4, which is 1/4, right? Or 4 to the power negative 1. And this is 4 minus 1 times, I'm sorry, this is the, what is that? 1/4 times 4x equals 1/4 times 3. Or x equals 3/4, right? Is that correct? And of course, this method fails to work for the equation like 0 times x equals 3, because 0 has no multiplicative inverse, right? Excuse me. And the generalization of this technique can be used to solve the square linear system, which means the number of equations are equals to the number of unknown variables, right? And to see why we are interested in the concept of a matrix inverse, suppose we want to solve a linear system AX equals B that has m equations and m unknown variables, okay? So suppose A inverse does exist. Then we multiply both sides of AX equals B by A inverse, okay? And we see that any solution of AX equals B must also satisfy A inverse times AX equals A inverse times B, right? And using the associated rule and the definition of a matrix inverse, we may obtain X equals A inverse times B. So this shows that knowing A inverse enables us to find a unique solution to a square linear system, okay? This is analog of solving 4x equals 4, 4x equals 3, right, that we've done earlier. Just by multiplying both sides of the equation by 1/4, right, this previous screen. Well, it's a bit early, but